Hello everyone. In this video, we are going to talk about thermal analysis in SolidWorks. So if you have an object like an I-beam, for example, and this object is basically this part is subjected to thermal conditions, thermal load, what we call, then definitely you can look at the temperature distribution within the part due to different modes of heat transfer and different thermal loads that are applied to the object. So for example, you can try to have a heat sink or a heat source element within the object, which is not super realistic most of the time, especially if it's a solid object like this. If it's like a room or something, yes, but the other modes of temperature and heat transfer that you can consider is if you can keep the temperature on an edge or a wall or surface or something like that constant. If you can consider conduction, which happens almost all the times, right? So through molecular vibrations, you can have conduction in all of the material within the material, and the formula for the heat flux or the heat energy per time, Q dot, is for conduction negative Ka dt over dx, where K is the conductivity coefficient for that material, A is the cross section, and dt over dx is the gradient of temperature with respect to location. And this negative ensures that the heat goes from higher temperatures to lower temperatures. The other mode of heat transfer that we have is convection, where the hot surface is exposed to a fluid, right? And so if the temperature of that wall that is exposed to the fluid is T sub W, and the fluid around the material, the part, the temperature of it is T ambient or T fluid, then the convection, the heat flux due to convection, Q dot, is given by H times A times TW minus T ambient, right? Where A again is the section, the cross section exposed to the fluid flow, T wall and T ambient I already explained, and H is the convection coefficient that you have for basically that convection by that fluid, which depends on so many parameters like the speed at which the fluid moves with respect to the surface. Like, for example, you might also call it the Reynolds number and so on and so forth, right? And the heat transfer also could be done through electromagnetic radiation, where the heat flux can be written as the product of two constants, sigma and epsilon, times A. A is the section, the cross section of the part that is doing the radiation. T of the wall again is the temperature of the surface that is radiating heat, and T of the ambient is the ambient temperature. Each one of them is raised to the power 4. And sigma and epsilon, what are they? So sigma is a constant called the Stefan Boltzmann constant, which is basically 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the 4. And this is basically showing the radiation, the heat flux of radiation for black objects, the objects that are doing the maximum basically radiation. For objects that are not perfectly black, like gray objects or any other color, then the amount of radiation is a fraction of sigma A TW to the 4 minus T ambient to the 4. And that fraction is shown by this coefficient epsilon, which is between 0 to 1. And we call it the emissivity coefficient, right? So that's the emission or emissivity coefficient of that object. So these are the three major heat transfer modes that we have for any object, correct? And as I said, we can also have a heat source, a heat sink, and a thermal load. So now how do we do all of that in SolidWorks? So here This is my I-beam, and now I go under Simulation tab and click on New Steady. And this time, instead of static or frequency, I go and click on Thermal Load. If I want, I can also use 2D simplification. So basically consider the beam as a 2D instead of 3D, and that is when your object has almost like a uniform thickness. This object does not have a uniform thickness. If you look in the X direction, the third dimension really, if you want to simplify it as only along YZ plane, then definitely along X you don't have a uniform thickness. Or you might say, well, I might consider it to be no, along the XY plane and not do anything about the depth of the part along the Z direction. You can, as long as the loading condition is uniform all along the beam. In this case, I'm not going to use a uniform loading along the beam, so I would not use 2D simplification, and I just directly go to 3D. Now, here you have the connection. If you want to do any connection, I don't want to. I just want to have the part free. So I have thermal load, and now, as I said, I can have temperature, I can have convection, I have heat flux, right? And I have heat power, I have radiation, and you might say, what's the difference between convection and heat flux? Because they look quite similar. And the answer is yes and no. So both of them have a Q dot term, but here this Q dot is kind of depending on the temperature of the fluid. So that exactly follows this formula here for convection. For heat flux, basically it's a constant Q dot that is passing through a specific cross section. So that heat flux, although the shape of it looks like convection, it's just basically a constant or specific input, but not necessarily through the fluid flow. And this is like constant temperature somewhere, right? So you might say, okay, what's the use of heat flux? Well, if I make heat flux to be zero on a specific face like this, what's the meaning of this? If there is no heat coming in and going out of a surface, what does it mean? It means that surface is sealed, insulated, right? So if we say, let's see if I can add it somewhere for you. When we say Q dot equals 0 for a surface, it means that surface is insulated, right? Or has thermal insulation, like what you try to do for the walls of your house, right? You try to use insulations and bring down these Q dots to the smallest number, right? So that's how you can do insulation, thermal insulation. So let's go ahead and apply something. So first, we make it as simple as possible. We go ahead and we try to do insulation on all of the side surfaces. We apply a constant temperature on the left, and on the right side we are going to have heat convection. Okay, so what's going to happen here? So let's go ahead and do it. So right click, heat flux, and here I make heat flux 0, so definitely it means there is no heat coming here or going out. And any side surface of this part, I try to do insulation on it. So nothing goes in and out from any side of this part here, like this. So all surroundings are completely insulated like this. So now I only have the front end and the back end, and now on the front end I'm going to apply a temperature. You can choose the unit to be Kelvins, Fahrenheit, or Celsius. So let's say I apply positive 200 degrees Celsius here, right? And I fix it over there. And then on the other end, as I said, I'm going to use convection here. So I say this other end, I'm trying to um, subjected to the, let's say, air or something like that. So I go to convection, and it says where? I say here. Then it says, okay, fine. What is your H, right? Convection coefficient, because it has A already. And then when it finds temperature at any point minus the ambient temperature multiplied by H, that's Q dot. So the other thing you need is the bulk ambient temperature. And here, since it is in kelvins, I make sure it is less than 200 degrees Celsius that I had on the front end. So, I have to add 273 to Celsius to make it Kelvin. So if I say, let's say 27 Celsius, that's like 300 Kelvin, right? So I have to say 300. So I make it like 300. So it's kind of like normal temperature, right? Outside 27 degrees Celsius or 300 Kelvins. The other side is now way more than that. And now you need H, and for H, what I can do is I can go ahead and get the H for the air, right? So I say convection coefficient of air, and it says depending on whether the air is just free convection, forced convection. So this is basically what I told you, the difference between the speed of the air. Are you basically using a pump to move the air over the object, or you just let the air on its stationary configuration to do the heat transfer? Because the faster the air moves, the faster it can get the heat away from the object, so the convection goes up. So if it's just free, then the number is anywhere between 25 to 2.5 to 25. So I use somewhere in between, let's say 12, 15 or something like that, right? So let's say 12 units or 15 units. And the units are all SI and everything. So there we go. So again, you see here, definitely the temperature is 473 Kelvin. Here is this side, the ambient temperature is 300 Kelvin. So your beam is definitely going to be hotter than the environment. No heat flux through any side face. So what you predict to happen is basically the heat from the left side or front side, I'm sorry, starts the temperature to go up all the way to the right side. The temperature keeps going up, and as it does, then you're gonna start losing heat from what? From the right side. The other thing you need to do is to mesh, and you can go and say create mesh, or you can just say mesh and run. So you have control in mesh creation if you want to use high density, low density, right? If you want to use based on the curvature or so on. So you have all the options. So here I just leave it simple, medium density of mesh and standard mesh, not curvature, because specifically here the part has flat sides, and then it does mesh it, and you will be able to see the mesh. If the mesh is not fine enough, you can go ahead and redo the mesh and then run the study. And here SolidWorks is using finite element analysis, FEA, to get you the temperature distribution within the part. And as you can see, at 473, which I told you on the left, the temperature is starting to go down and further reduce until you go to that other side where it is what? 469. Okay, so, and this is basically what you see here is the steady state solution. Okay, basically after, because you have some initial temperature, right? And the initial temperature keeps going up on this side, because this side, the very edge of it is always 473, but now because of conduction, the heat starts to go, the temperature of the other side starts to go up, but you have some loss on the other side. And so you see now at the end of the day, when you go to steady state configuration, the temperature difference between the two sides is from 743 to 467. So it's just 6 degrees Kelvin or 6 degrees Celsius difference between the two sides. Now, in many applications, simulation in SolidWorks, you can go to the results, right click, and animate. And you might say, well, can I do animation here? And the answer is what? Guess what? Probably not, huh? If you do it, it says it's not available for this type of plot. Of course not, because here is a steady state solution. Here is when time has passed enough and there is no change versus time anymore. So time has no meaning, so animation has no meaning. So if you want, you can use the probe and let's say measure the temperature at a specific location. So let's say here, if I'm interested somewhere here in the middle of the beam, I can just use my probe tool, and at the specific location, I just go ahead and click. And then it shows me the value of temperature. Over there is basically 470.5, right? So you can use your probe tool and so many other tools that I showed you earlier, right? You can do ISO clipping and so on and so forth, right? And you can also go and change the definition of the way that this thermal plot is acquired. So you see it is based on just pure temperature. Now, could instead of temperature, you made it to be heat flux? Sure, you can. Could you make it to be temperature gradient? Sure, you can. So let's say I want to have a heat flux in the Z direction, which is along the beam, right? Instead of that. And I do it, and now you have to run the study again, right? So let me run that. And if you look here, the matter of fact is, if you look at the numbers, it goes from negative 2.5 e to the 3 to negative 2.5 e to the 3. So what does it mean? It means really the heat flux is almost the same all over the beam, right? Although it's kind of a little bit confusing showing it with two different colors, but the matter of fact is the heat flux is almost the same. So if you click here, you see the number is negative 2.5 e to the 3. If you click here in the green area, that's also negative 2.5 e to the 3. So it's kind of like a graphic issue, really. There is no red color. The only color you have is green, and it's kind of uniform heat flux, right? It should be, because now it's a steady state, so everything should be kind of the same, and you can look at temperature gradient and so on and so forth, right? So feel free to modify what you want to see. Most of the time, as I said, is temperature, but you can basically look at anything else, right? So now let me run this for you one more time. And again, here, although it is showing three different colors, it's not really. If you look at the max and mean on the legend, they are the same number. So also the temperature gradient in this direction, dt over dx, is the same. But now we can do a lot of other things, right? If we allow some heat flux to also happen along the way, then it kind of eliminates the balance that I have here, and this kind of uniform gradient temperature or uniform heat flux that you see, that's going to go away. If one of these surfaces that are insulated, I can get rid of it or replace it with another mode of heat transfer, that's going to change everything. So what I can do is I can go ahead and go back here, and let's say when I go to this heat flux, then I just get rid of one of the faces. So let's say this one of the faces, maybe, let's see which one is the top face. We can find it. That's probably this guy, maybe or maybe not. No, it's most probably, let's see, no face. Which face is it? So if I can find which face, it's this guy here. There we go. So I got rid of it, okay? So, and now can I replace that with something else, this top surface? So if I right click here and say I want to replace it with radiation, maybe this top surface of it is going to do some radiation. And it says, okay, do you want surface to ambient radiation? And say, sure, here. And it says, okay, fine. What is the ambient temperature? And you say, well, maybe that's also 300 Kelvin. And then it says, okay, now what about the emissivity? And that is that epsilon that I told you. Do you want it 0? Do you want it 1? Do you want it somewhere in between? Let's say I would put somewhere in between 0.5, right? So now this top surface also does radiation to the environment, correct? And now if I run it again, now you definitely will see some different numbers, some different shape and everything. So let's take a look at the results. There we go. So now, last time, if you remember, it went from 473 to 467. This time it goes to 453. So now your temperature drop is 20 degrees Kelvin instead of 6 degrees that you had last time. And that's obvious because you are now losing a bunch of heat on the top surface as well, right? And now if you go ahead and change this to change this definition to something else instead of this, let's say heat flux in the z direction. Now if you look at heat flux, you clearly see that the numbers on the legend are not going to be all the same number. If you remember last time, I only had one single number for heat flux or one single number for temperature gradient. This time I have a range. Goes anywhere from 1.6 negative times 10 to the 4 to negative 2.2 10 to the 3. Okay, so anywhere from negative 2200 to negative 16,000 is the heat flux, and the heat flux is much bigger in terms of magnitude here in the beginning than toward the end, because here the temperatures are higher, and when you raise the temperatures to the power 4, it means the heat flux and the heat loss due to radiation is much bigger in the beginning compared to the end. This time the relation is not going to be linear along the beam because this nature of the radiation is not linear with temperature, it's to the power 4. So that's why you see it drops, and it drops significantly from negative 16,000 to negative 2,200. Okay, so hopefully it does make sense now. What's the meaning of this non-uniform temperature or heat flux distribution? And just for the last thing before we finish the video, I want to also show you heat power. So here I go to that heat flux and I get rid of this bottom surface as well. So the bottom surface is also not insulated, but instead I would like to what? I would like to apply a heat power to the bottom surface. And it says, okay, how many watts? You say maybe I want 500 watts applied to that face. So now it is a heat source, a heat power that is also created from the bottom, and it's like you're heating the bottom of the beam. So if that's the case, and if I run the steady, now what would you see different compared to last time that you had the radiation on the top and the bottom was insulated? There we go. So now look at the difference. Last time the temperature here that you had was 473, and here it was like 453 or something. So I had 20 degrees Kelvin drop from front to the back. Now if you look on the right hand side, instead of having that big drop, guess what? You have what? You have 846, 47. So now the right side, which was the coldest part of the beam, now this time it is actually the hottest part of the beam. Because now you're adding more and more what? Heat from the bottom of the beam to the beam. So this time the nature of the problem is what? Quite a bit different, and maybe 500 watts was just a little bit too much, but even if I just go and make it 100 and run it again, you still see that now that heat power that is added kind of all over the beam is definitely bringing up the temperature all over the beam, except for the left end, which you try to keep it constant. Okay, and that's not really realistic. It's not easy to keep the temperature of a surface fixed in reality, even though you might use controllers and something. Just a very thin surface to keep it constant temperature, and the rest of the material does change, not as trivial. So now you see the other end is now 540 instead of last time it was like 800 something. But clearly you see that the temperature of the entire beam is gone up because you're adding a power heat on the bottom, right? So this is just some basic thing. And then as I told you, you can do ISO clipping, section clipping. You can look at all sorts of chart options for this temperature, right? You can show min and max annotations, correct? And everything that might be useful to you, correct? So here, if you just apply those, it shows you where in the beam and how much is the max and the min temperature, right? So there are lots of things that you can do when it comes to looking at the results of your study. So hopefully this video was useful to you, and I will see you in my next lecture. Thanks.